guy next week. Be able to use by hand. Like I said, today's processors have trillions and trillions of transistors inside. So, like I said, this first one is known as type A. Like I said, today we use CMOS chips, which use P-type and N-type. So that's where we kind of ended on Friday. I ended up on the OR, right? Last gate I did, was it? The OR?
Yeah.
Okay. So we're going to do 3 more useful logic gates for this class. So next one is NAND. Just remember it as not AND. The gate looks like this, 2 inputs, same as the AND, but we put a little knot in front of it. Looks like a little circle is a knot. So then the gate looks like. And the arithmetic is we need to do A and B, the knot on top, a bar, or we just do A, B, bar on top. Right. And the Venn diagram looks like this. So we have.
What was the stuff in like the C program?
There isn't one you want to think of it as.
Okay.
The only way to do it in the C program would be like A, and it would be not in front. There's no way to do it. So if you have A and B, so AND was everything inside, everything that A and B covered. So the not AND was everything opposite of what the AND covered. So everything inside here but the middle part that A and B covered. So the truth table is so regular AND, we got 0, 0, 0, 1. And so a not AND is all we have to do is basically not the result of an AND. So we get 1, 1, 1, 0. So that's the result of the NAND gate. Then we have the NOR gate. Same as that, not OR. Got 2 inputs, so the same as an OR. We put a little knot in front of it. This comes to a point. And now we add A or B, not, or A or A or B on top.
Is that supposed to be
Is that just
NAND or AND?
And B, sorry, not. Yeah.
And then not it, right?
Yeah, so as I said, this one here is the we not that part. You say here's the AND gate, and I separate.
So it's an AND gate and then an inverter, right?
Yeah.
Okay.
But we go to the circuit. First circuit I draw the transistors. First circuit I drew the transistor, we created the NOR first, and then we knotted this to make the OR. Inside it's actually opposite what you think. So inside is actually, inside that OR is actually a NOR with a knot on it to get the OR. Makes sense? Okay. So the Venn diagram is so the OR was basically everything that A and B covered. So a not OR is everything outside of A and B. So everything on the out. And the truth table so here's the ORs. We got 0, 1, 1, 1. So then the NOR is going to be 1, 0, 0, 0. And the last one. Exclusive OR. So it has a line like that, and then it goes into the, just like the NOR gate. So our exclusive OR looks like. I think the other day I did a mistake. I think I told you that was a not OR, an OR. This is exclusive OR. Simple for exclusive OR. A or B. So basically the definition of exclusive OR is one input has to be 1, but not both. So basically is the inputs are both 1, but not, both are not 1. So basically everything that A covers, everything that B covers, but not what they both cover is what exclusive OR is. So the truth table looks like this. So like I said, both are not true, so it's false. One's true, so it's true. One is true, so it's true. Both are true, so it's false. So that's our exclusive OR gate.
Then how would we write that in C?
Not quite sure on that one. Never had to use exclusive OR.
Oh, good. That's useful.
I believe they do have one. I'd say probably have to look it up.
They're saying don't remember it.
No, I don't remember it. This is more like for me, for your usefulness. I'm not going to test you on the C syntax, and so I just find it kind of useful when you actually program something else in a higher level language to use those. So okay. So now what do we do with these gates? So we're going to draw a logic circuit. So I'm gonna have three inputs. And I'm going to add the first two together and the last two together. I'm going to OR them together. Then I'm going to get some output. Right. If you look at this, so this is a circuit diagram or logic diagram of this circuit I have. I can also represent it as a function. So f equals a, B, R, C, and D. So A and B, R, C, D. What we see that is, this is AB, this is CD, and this is A, B, R, A.
Or plus?
Or. Yeah.
Or?
Yeah, this is OR.
Oh, that's right.
Yeah. So, like I said, I can put a dot in here for the and. I'm just gonna leave it without the dots. So A and B are C and D. And so basically, that's my function of the circuit. So I could either give you a circuit like this, ask for the function, or I could give you a function and ask you to draw a circuit. Right?
Quickly, can you do like an order of operations with the different logic gates for example?
Let's do it by level, don't you?
Yeah, same like algebra kind of thing.
Alright.
So basically, is you want to do like this? S's. So basically, is you do multiplication first, and
What about knots?
then we not first. Depends on what. Depends on. Let me do some more examples.
Okay.
It might be clear. So then we can also do the truth table of this function. So we have to put A, B, C, D. We'll do A and B first. We'll do C and D. And then we'll do E. E or. So.
AB plus CD.
What's that? Yeah.
Not too correct here.
There we go. Sorry. So then, this way. So we have 0, 0, 0, 0 on these lines. So 0 and 0 added together is 0. 0 and 0 added together is 0. 0 ORed with 0. 0. So then here we got 0. Here we got 0. And here we got 0. So let's do. One. So now D is 1. This didn't change, so let's stay the same. 1 ended with 0 is 0 still, so it's still 0. So our output's still 0. I'll do 2 more of these. Now C is 0 and D is 0. Hopefully you can tell these didn't change. 1 and with 1 is still 0. 0, 0, 0. So everything's still 0. Then get 1, 1, 1. And so now we have 1 ANDed with 1. 1. 1 ORed with 1 is 1. So now we get an input of 1. An output of so that was 1, that was 1, that was 1. Right? So I can look at the circuit and start putting the numbers in the truth table and putting the numbers in the outputs and going through the whole circuit. Or I can say I can look at the function and compute the results. So then if I go, so then I go A, B, so we draw a line down the middle. One end with 0, still 0. 0 ended with 0, still 0. 0 ordered with 0, 0. Same with these. Ended with 1, still 0. Ended with 0, 1, 0, 0. Here we see it as 0, 0, 1. So here we got 1 and 1. So you get 1, 1. Basically, you can say is anytime C and D is output is 1, or A and B output is 1, my output is going to be 1 as well, right? Everyone got this one?
That second to the last one where it says 0, 1,
Shouldn't
1,
that be
0.
Yeah.
Wouldn't that be 0? No.
This one here?
The next one,
This one?
yeah. Shouldn't,
No, that's right.
No.
The output.
That's why this. I go. So A is 0, B is 1, C is 0.
C is 1.
C is 1.
C is 1 and D is 0.
Yeah. So one ended with 0 is
It's or, you don't have a 1.
0. And
0 or 0 is
0 and 0.
Is 0. It's still or, so.
Yeah.
No, we have 1.
So should be 0.
It's still 0,
Output.
0 or 0, 0.
Output is showing 1 for that one, right?
Oh, my bad. I see what you're saying. Okay, my bad. I didn't. Yeah. I bet.
Okay.
I thought you said it was supposed to be 1. I'm like, no, it's supposed to be 1. So, like I said, you can fill out the rest of it. I'm not going to fill out all the rest of them. So this is kind of an example of what you can see on a problem, what you need to do. I could ask you, here's a function, fill in the truth table, draw the circuit, or give me the function of the circuit. So the kind of questions I can ask.
Would you give us the symbols, like, because I would not have known that was an OR function.
This one here?
Well, by that, yeah, but in the function, the plus sign, I would not have known that.
It's kind of like a
Yeah,
discrete math.
Yeah.
confusing.
Like I said, it's one of those ones where you just have to memorize it or learn it, right?
And then the circle around it's the exclusive or.
Yeah. So I can put A, B, R, C, D.
You could also think of it as, if what's 0 plus 1, that's going to be 1. If it's 0, if it's 0 times 1, that would be 0.
I wouldn't do it that way, but I know some people say it's clear that way. Like I said, one of those ones where that's why they call it logic instead of basic mathematics. They call it logic. But only you're using the same symbols in regular mathematics to do logic math. So I know it's.
You'll get into trouble if you start doing 1 or 1, you know, and okay, it's 2.
Yeah.
It's still 1.
Yeah, that's what I said. I kind of try to stay away from doing that.
I always think in terms of 0 and 1, 0.
Yeah.
I don't use 2 and 3.
Yeah.
1, 1.
And it's 2 to the power of variables, right?
What's that?
2 to the variable power, like you have 4, so it'd be 16, right? 16.
Yeah, it'd be 16 answers on that problem. Okay. Now, we do circuits. We draw circuits, I give you the functions of circuits. Now we can figure out if we can actually make a circuit smaller or reduce it, make it basically cheaper to build. So that way we can solve the circuit is cheaper to build by reducing how many transistors we use to build a circuit. And so we call these the laws. Laws of Boolean algebra. And they're just like our algebra, regular algebra laws. So we have the first one is the combinational law. That is with 0 or 1, also known as the identity law. So there's two types of functions we can get. We can get what is known as sum of products, abbreviated as SOP, and we can get products of sums. Like I said, we're using algebra terms to do logic. So this one is POS. So the first law in sum of products form is that if A ORed with 0, no matter what, equals A. Alright? So if I do the truth table, at A 0, so at 0 or 1, so OR together, so no matter what, we get 0, 1. So basically this is A. So that's why we say no matter what, any input ORed with 0 is always going to be the original input. And so A ORed with 1 equals 1, no matter what we do. Hope we can see that one. So if I change this to all 1s, and OR, we all get 1 ORed with 0 ORed with 1 is 1, 1 and 1 ORed with 1 is 1. So no matter what, our answer is always going to be 1 on the output. So you can see this for this. This tells me it's a sum of products, basically your algebra. The summation of different products. So we can make this A could be a product of another product. So SOP is the product of sum, so you do A ANDed with 0 equals 0? Yeah. Right. So then if I put zeros here, hopefully you can see we're doing the AND operation this time. So 0 ANDed with 0 is 0, 1 ANDed with 0 is 0. So no matter what we do, our output's always going to be 0. And then the last one, ANDed with 1 equals A. So I put 1. Zero ANDed with 1 is 0. 1 ANDed with 1 is 1, which is the same output as A. So that's why we get the result as A. So that is the combination. I'm going to always call it the identity matrix, the identity law. That's the way I learned it as. And next law is the commutative law. A plus B, sorry, A or B equals B or A. Right? Let's say algebra, you do A plus B equals B plus A. Same thing, algebra, and then we can have A and with B equals B and with A. You just want to think of it as, all I did was switch the inputs on the gates, it doesn't really change a thing. So that's the commutative property. Now we have the associative. We have A or with B or C is the same as A or with B or C. Then we can have A and with B and with C, which equals A and with B and with C. We have the distributive property. So we have A and it would be RC equals A and it would be or A and it would C. Then we can have A or B and C, which equals A or B and it would A or C. This one I can never pronounce correctly. Manipulate by that. We got A or with A equals A. And B and it with A equals A. Okay. Everyone have these down? I'll try to leave the last couple ones up. Okay, we have involution, revolution. So I can have A not equals A. I'm not going to do the other one because that's what it is. Works for both, same thing. We said, so we not and a not, so it's just A. And second to the last is the commutative, complementary law. So I have A or with A naught equals 1 and A ended with A naught equals 0. Okay. So the last one is kind of a law in itself. Give it its own separate name, so this is called the Morgan's Law. basically is we can get from SOP to products of sum. Basically, we can convert a function from products of sum to sum of products. So formula looks like this. So A or B or C, blah blah blah. And I not that whole function. So I not basically this is my function in here. F equals A or B or C. And I not that function. It equals A naught B naught C naught. So basically what we do is I go in and I not everything, even the gates. And then we see the gates is that we reverse. So it was or, now I make it an and. So that's why we went from A naught and B naught and C naught. So that law makes me convert basically this function here to equivalent products of sums. So I had sum of products. I converted it to products of sum using De Morgan's law. So those are our laws. Now we get to apply them. I'm going to start with a simple one. So here's my function. I have input A and B, and it equals A or B A naught. Alright? So if I look at this, I can see right away, I can apply De Morgan's law on this part of the function right here. So I'm going to use De Morgan's law. So I'm going to convert B A naught. So it's going to be B naught or A naught. So then now my function looks like this: A or B naught or A naught. Okay. Anyone can see what law I can use next?
Commutative?
Yes.
Derivative or whatever.
Commutative property.
Not associated.
So what was the commutative property is? So then I can say that
A or not A or not B.
yeah, A or not A or B naught. So what's this right here then?
One.
1, which is what law?
That's one.
Complementary law. So A or A naught equals 1. So now we have 1 or B naught is now our function. And then this is the identity law. So 1 ORed with anything is 1. So the answer to this is 1. So if I drew this out, if I drew this original function out of the circuit, so we have A and B. So we have A and B and together, that inside here. Then I need to knot it. And then I need to OR it with A again. So then I draw another wire over here and we OR them together. Alright. So that's basically to create this function, I have to draw this circuit. Or, since we did our Boolean algebra on it, all I need is that. Basically, is I just need a wire with a 1 on it. Some kind of voltage on that line. So basically, I don't even need that. I don't need to use any transistors to build this circuit.
Isn't Boolean algebra would be more useful for seeing how a circuit works versus creating a circuit, right? Because if you're creating a
Well, yeah,
circuit, you already know what it is. You know what you want your outputs to be.
Some are useful for reverse engineering something. Let's say you just have the schematic, and you're like, what's the function? And then can we make it actually smaller? Basically, that's how AMD kind of works. AMD used to be a daughter child of Intel, and they redesigned the Intel's chips, reverse engineered them, and made them better. Basically, is they reduced the circuits in the chips, which actually made them faster. And so, we won't go into how electricity flows through these transistors. So we'll do one more example for today, so I won't bore you too much on doing this. Start again on some more Boolean algebra. So we have the function AB, and we have A and B naught, and with A naught or B. Ended with B naught R B. So A and with B naught, A naught, or with B, ended with A naught or B. So I'm gonna draw the circuit first. So we got A and B. So this one's more of just trying to figure out how you want to do it. I'm going to do inside stuff first. So if you want to think of it as this right here is just as A, B, and then you knot that over. So we got A and with B. So we have A and with B, and I need to knot it. So that's this part of the function. Those two.
Can't you just put a circle at the front of the knot?
Yeah, we can. One of the things is I could say is I only have and or nots, and so I put a circle there that says I have an AND gate, and so I only have and or the knots. So then we do the inside one. We have A naught or B. So then I got to take the A down, not A, take the B, and we're ORing these together. So I OR them together. Then I have E I'm gonna, let's keep drawing down. Then we can do a trick. I'm gonna say I have a three input OR gate, so then I can put all these into one giant AND gate. Alright. So there's my circuit. I could also I could have done it this way. Do the same thing. If I do AND that one together, then AND those two together. Basically saying is AND these two guys together, and then add that result to that one. So there's our circuit for it. So we want to reduce this function, right? What do we see first? What's the most simplest thing we can reduce now?
B naught or B?
Yeah, B naught, B naught. So that one is what?
One.
1. So that would be the complementary law. So we know that B naught or B equals 1. So now our function is A, B, A naught, B, 1. Okay. What can we reduce down? Anything else?
A naught or B?
What?
A naught or B?
A naught or B?
Can we distribute them?
Just B?
No.
It's not.
One ORed with one AND with anything is basically the function, right?
One and with something?
One, yeah, well, and we're doing this part right here. So one ANDed with this whole part
Oh,
is
it's the function.
itself.
Yeah.
So basically, it's using the identity law.
Wasn't that what or though? That's about one or something gives us something. One and something. The other one has to agree.
No. One ORed with one is one. One ANDed with something is a.
Is something.
Oh,
It's something, yeah. So, okay, so basically, so we get rid of the 1.